We are going to discuss acids, bases, and neutralization. So, the first thing I'd like for you to think about is, what do you think about when you hear the word acid? Okay. Sometimes we see commercials on TV for acid reflux or GERD. And so you see Tums or you see Nexium. Nexium was known as Nexium, the purple pill. That was kind of their tagline. And then we also have something like Pepto Bismol. These are all things that help acid indigestion or relieve acid or heartburn. So, what is acid indigestion? And what does that have to do with your stomach? So, something I'd like for you to think about is, in the United States, we actually have a larger production of these medications than in other countries. So one day I traveled to Australia and I had forgotten some of my acid reducer medicine. And I went into a pharmacy down there, and it was very difficult. It was a lot more difficult than when I was there to find an acid reducer, an over-the-counter substance. Okay. And so you got to think about like American culture and what are some of the effects or causes that cause our body to have this overproduction of acid or these stomach problems. So acid reflux, sometimes you might get heartburn, and what that feels like is it's like that like burn in your chest, or like, sometimes you burp and you kind of like throw up a little bit in your mouth or something, and you might be thinking, oh, that's so disgusting, and it's true. But that happens to a lot of people. And think about the last time that ever happened to you. What caused that? Okay, what caused that? Now, when you're thinking about that, you might think, well, I was really stressed at that time. And that could cause acid indigestion, or maybe you ate some really spicy food, or you ate some really greasy food. You maybe ate something that your body doesn't process correctly or something. So what does this have to do with your stomach? Well, your stomach requires acid to break down food, right? So you have stomach acid, and that helps in the digestion process. Now, what ends up happening is sometimes our body produces too much acid. Okay. And the reason for that is, if you think about it, acid can break down things or kill things, right? And so your brain might trigger your stomach. Something's wrong. Something's very wrong. And I need to balance myself out. So I need to get to this place of balance. I need to fight this infection or fight this problem in my body. And the problem in your body is the stress. You're stressed out, or you're overwhelmed, or you're anxious. And so your body is going to fight that, or try to, by maybe an overproduction of acid. Sometimes you can overproduce acid by eating the wrong things. Things that are highly acidic. Okay. So how do acid reducers work? Well, an acid reducer is going to reduce the acid by, maybe you're thinking, neutralizing it. An acid reducer will neutralize the acid in your stomach. Another thing that an acid reducer can do, some acid reducers are going to be bases that are going to neutralize. So like Tums is calcium carbonate, which is going to end up neutralizing the acid. When it comes to something like Prevacid or Prilosec, those are called proton pump inhibitors. So it inhibits the production of the protons. And when we say protons, sometimes that's another word that's synonymous with acid. So a proton pump inhibitor will slow down or inhibit the overproduction of acid in our body. So those are two different ways that an acid reducer can work to solve this problem in your body. But we need acid. We need acid for the digestion of our food. So we can't just completely get rid of the acid. Acid is not a bad thing. And maybe in the concentration discussion, you realize that too much of something could be bad for you, but it all depends on the concentration. So what are some different types of acids that you have around your house? What can you think of some acids that you have around your house? Things like lemon juice, or things like lemon juice or ketchup, maybe. Things that you might not think about. So I've had to cut things out in my body, and some of those things that I've had to cut out in my consumption are like spicy foods or fried foods, Mexican food, burritos. I've had phases in my life where I've had to stop eating those things because of the overproduction of acid in my body. So those would be some acids, lemon juice, vinegar, something like that. And think about the properties of those things. That's what we're going to talk about next. And then what are some bases in your house? Okay. Think about some bases. Well, some examples of bases would be like drain cleaner, window cleaner. Things that are cleaners are often bases. Okay. Those would be some bases that are found around your house. So if we spend some time discussing acids and bases, some properties of acids, remember we said that citrus fruits are acids or have acid in them. So citrus fruits, when we think about them, they have a sour taste. Acids tend to taste sour, they don't feel slippery, and they have a pH of less than 7. Bases taste bitter, they feel slippery, and they have a pH of greater than 7. Now, bases tend to be found in like the cleaning solutions in your house, or like soaps, or if you think about like shampoo and conditioner and stuff. Now, when we put an acid in water, it releases hydrogen ions, or H plus ions in the aqueous solution. When we put a base in water, it releases hydroxide ions, or OH minus ions. Acids, when you bring them in contact with metals, they'll corrode the metals and they'll react with the metals to produce a compound and hydrogen gas. Whereas bases are not going to corrode metals and they're not going to react with metals to produce a compound and hydrogen gas. Finally, there is a little strip of paper that you can use to tell you if you have an acid or a base. It's called litmus paper. And when I put litmus paper in an acid, it turns the litmus paper red or pink. If I put the litmus paper in a base, it's going to turn it blue or purple. So if you've ever heard someone use the phrase like do a litmus test, you're kind of getting an idea, getting a feel of the situation. Okay. Now, another thing for you to recognize is that when I add an acid and a base together, when you mix an acid and a base, they are going to end up reacting to produce water, so H2O, and a salt. Now, when I say a salt, I'm not talking about just sodium chloride. If you recall, when we talked about ionic compounds, a salt is any ionic compound. So any compound that's made up of cations and anions. When acids and bases react, they produce water and a salt, some kind of ionic compound. So how do you know if you have an acid or a base? And you'll see these hydrangeas right here. Some people love hydrangeas. Hydrangeas actually tell you what type of soil they're in, they're being grown in based on their color. So if a red hydrangea is there, red or pink, then you know that the pH of the soil is less than 7 or it's acidic. If the hydrangea is more blue or purple, then you know that the soil is more basic or at a pH of greater than 7. Now, some other indicators that we have are cabbage juice. You can use red cabbage juice. That's a natural indicator. If I drop some drops of red cabbage juice into like lemons or lemon juice, that's going to turn like a red or a pink. If I dropped it into like bleach, it's going to turn like a blue or a purple color. Okay. So an indicator changes color to indicate if it's an acid or if it's a base. Litmus paper is another one. Hydrangeas they're not indicators, but I put that as an example here because you see a color difference based on the pH level of the soil that you're growing in. And then also universal indicator. Universal indicator turns different colors based on the pH of the substance that it's been dropped into. So universal indicator will turn red if it's dropped into a substance that has a pH of 0 to 1. If it turns red-orange, it's a pH of about 2, orange 3, orange yellow 4 to 5, yellow 6. Once you get to that green color, you're looking pH of 7, and then blue green is going to be 8 or 9. blue 10 to 12, and purple 13 to 14. So you see here that an indicator is going to turn, in a lot of cases, will turn more red if it's an acid, more blue, purple if it's a base. So if you look at this diagram right here, you can see different things that you might find around your house that have different pH values. So for example, something that's more acidic is going to have a pH of 0 to 6. And something that's 0 to 6, some examples would be battery. We have stomach acid here. We have a lemon here, or lemon juice, vinegar, tomatoes. So that would be tomato soup, ketchup, anything, a salsa, that kind of stuff. Coffee is a 5. Milk is actually slightly acidic, which most people say that milk is basic, and that's actually not true. Milk is going to be slightly acidic at a 6, but it's closer to neutral. And then we have water is neutral at a 7. Then your blood has a pH of closer to 8. So we're getting closer to a base here. Stomach tablets are right here. When I say stomach tablets, that would be like your Tums. Then you have ammonia solution, which would be a cleaner. Soap is a 12, bleach is about a 13, and drain cleaner is a 14. And that's more alkaline. And something that's alkaline is going to be a base. So our acids range between 0 and 6 on the pH scale. Our neutral substances are at a 7. So an example of a neutral substance would be pure water at 25 degrees Celsius. Pure water at 25 degrees Celsius is going to be neutral. And then we have bases, and bases are going to be between an 8 and a 14 on the pH scale. And that's what the pH numbers represent in terms of acids and bases. So when we talk about acids and bases, what if we put an acid or a base in water? We did already talk about this a little bit, but a hydrogen ion in water, if we put acids in water, they're going to add hydrogen ions to the water. And if we put bases in water, then we're going to add the OH minuses to water. So for example, we have HCl. And when we throw that into water, you'll see right here, this AQ means aqueous. It's an aqueous solution. So it's in water, and these ions dissociate. They break down into their ions, their ion form. And so for HCl, which is hydrochloric acid, you have your H plus in solution and Cl minus. Here we have a diprotic acid, which is sulfuric acid. H2SO4 diprotic means it's 2 hydrogens. So 2 H plus ions and an SO4 2 minus, but there's your H plus right there, indicating an acid. Now indicating a base, something like sodium hydroxide dissolved in water is going to dissociate to Na plus and OH minus. So that OH minus is going to indicate a base. Here we have magnesium hydroxide, where we end up having 2 OH minuses and 1 Mg2 plus. And then we have something that's neutral. So something that's neutral would be like a salt. This is table salt, Na plus and Cl minus, and that's going to end up being something that is neutral as it ionizes. So this ionization idea brings us to the idea of acids and bases and the strengths of their acids and strengths of the bases. So a strong acid is an acid that's going to dissociate completely, meaning all of the ions are going to split up. They're not going to stay together, in this case, as the HCl together. They're going to split up into your H plus and your Cl minus. They're going to completely ionize. They're very good conductors of electricity. So strong acids are very strong electrolytes. And so you end up having a complete dissociation of your acid, whereas a weak acid is going to be one that's not going to completely dissociate in water. And so you're going to be left with more HFs than H plus and F minus. Okay. Or polyprotic acids. Polyprotic acids would be more than one H plus in the solution. And also organic acids are tend to be weak acids. So for example, your vinegar is acetic acid, and acetic acid has this, it's called a functional group, and it's a carboxylic functional group. Those are organic acids, and they tend to be weak acids. Now, strong bases goes along with the same idea as strong acids. Strong bases also are going to completely dissociate in water. So an example would be sodium hydroxide is going to completely dissociate. So Na plus OH minus. Now, your best indicator for a strong base would be if the base is made up of an alkali metal or an alkaline earth metal as your cations. And then a weak base would be like an organic base. So like ammonia, NH3. NH3 is going to be a weak base, but notice you don't see an OH minus in there. And we're going to talk about that in a few slides. But this right here would be an indicator of a base. It's just going to be a weak base, and that means that it's not going to completely dissociate in water. Some of the compound will stay together. So water and hydrogen ions. When I look at water can split into H plus and OH minus. And you look at that, and that gives you H2O. So H plus OH minus gives you your H2O. And if you remember, we talked about neutralization reactions where you're going to produce a salt and water because your H plus and your OH minus come together to form H2O. So what does this do? Well, this actually tells you, if you look at the hydrogen ion concentration and the hydroxide ion concentration, then you end up getting 1.0 times 10 to the negative 14. And that's the ion product constant for water. So if you take the hydrogen ion concentration and the hydroxide ion concentration and multiply those, you're always going to get 1.0 times 10 to the negative 14 molar. So there are a couple of things to look at. Number one, these brackets around the H plus just means the concentration. So this would be hydrogen ion concentration with your brackets. This would be hydroxide ion concentration. Now, those are measured in molarity. The unit of measurement for hydrogen ion concentration or hydroxide ion concentration is molarity. Now, you'll see here in this little line right here, I also say H plus or H3O plus. That's just another way to write your hydrogen ion because your H pluses add to your H2O in solution. So you end up getting H3O plus, which is an acid, and that is called a hydronium ion. For the purpose of this course, hydrogen ion concentration and hydronium ion concentration, those are synonymous with each other. They mean the same thing. They're going to be interchangeable with each other. Okay? So we look at these hydrogen ion concentrations, and that helps us determine what pH is. So where do we get the pH values from? And that's what we're going to look at next. So I would like for you to draw this chart down in your notes. And what this chart is showing you is the calculations to find your hydrogen ion concentration, your pH, your pOH, and your OH minus, or your hydroxide ion concentration. And to go from your hydrogen ion concentration to your pH, you would plug in the value negative log H plus. So say my hydrogen ion concentration was, say it was 1.0 times 10 to the negative 5 molar. So what I would do is I would plug into my calculator negative log of 1.0 times 10 to the negative 5. And everyone's going to have different calculators. So this is going to look a little bit different on everyone's calculator. For me, if I'm going to plug this into my calculator, what I would actually do is I'm going to actually type into my calculator 1.0 EXP. Remember, EXP represents the times 10 to the. So I'm going to type in 1.0 EXP negative 5. Okay, make sure that you hit the negative button and not the minus button. And then I'm going to hit the log button. and the negative value again. And that's going to end up giving me a pH of 5. Okay. Now, if I wanted to go down from pH to pOH, I know that pH plus pOH is going to give me 14. So 14 minus pH, which is 5, is equal to my pOH. So minus pH equals my pOH. So 14 minus 5 is going to give me a pOH value of 9. And then if I wanted to go to my OH minus concentration, okay, so this is my hydroxide ion concentration. Okay, if I wanted to go to my hydroxide ion concentration, I have two different routes that I can take. I can take this route from my H plus down to my OH minus. Okay, and in order to do that, I would do 1.0 times 10 to the negative 14 divided by my H plus, or my hydrogen ion concentration, which if I went ahead and plugged that in, then that's going to end up giving me, I'm going to look at 1.0 times 10 to the negative 5. So 1.0 times 10 to the negative 5 molar. Okay. And that's going to end up giving me a value of 1.0 times 10 to the negative 9. Okay. And that's my hydroxide ion concentration. Another way to do that is to do 10 to the negative pOH value. So I would do 10 to the negative 9, okay, which can also be written as 1.0 times 10 to the negative 9. But not all of our values are going to be so easy. So what I would do in this case is I would type into my calculator, for my calculator specific, I would type in 9 negative, and then I would hit my shift button and my log button, because above my log button I have a 10 to the X button. So that button is written as 10 to the X. So I would type in 9 negative 10 to the X equals, okay, or answer. Okay, and that's going to end up giving me 1.0 times 10 to the negative 9. You're going to have a few of these practice problems to work on while you go through your problem sets for this week. So calculating the pH and the pOH. If you didn't catch all of that, the calculation, the equation for pH is negative log of the hydrogen ion concentration. pOH is negative log of the OH minus concentration. If you have not gone through logarithms in your math class, this is basically a function, and we have, for example, y equals negative log x. And if you don't have anything written in this area, then we assume that that's a base 10. Okay. And so what this means is 10 to the negative y is equal to x. So 10 to the y equals x. And because we have this negative button, or this negative value, it's 10 to the negative y, okay? And that's what logarithm is. So y equals negative log x is the same as writing 10 to the negative y equals x. So that would be our way of finding, if we wanted to find what our y value is, we would plug in log x to get that, okay? H plus and OH minus, multiply those two to get 1.0 times 10 to the negative 14. How are pH and pOH related? Well, pH plus pOH equals 14. pOH is equal to negative log of the OH minus. So if we were to substitute our pH and our pOH, we get negative log H plus concentration is equal to negative log of the OH minus concentration. So what is the pH of a solution with a hydrogen ion concentration of 3.4 times 10 to the negative 4? So I want to plug that into, I know my pH is equal to negative log of my H plus concentration, which I've been given here. So that's 3.4 times 10 to the negative 4 molar. Now, what do I plug into my calculator? I'm going to plug in 3.4 EXP, which is my times 10 to the negative 4. And then I'm going to hit my log button and my negative button. And that gives me a value of 3.47. 3.47 is my pH in that situation. Okay. So calculating your H plus and your OH minus. When the pH decreases by 1, what's happening to the amount of hydrogen atoms or the hydrogen ions? That really should say ions there. And what is it doing? Well, it's increasing by a factor of 10 or by a power of 10. Okay, so what is the H plus of a solution with a pH of 4.5? So remember, we're going from we're looking for our H plus. So we're going this way in our chart. Okay. And we have 10 to the negative pH is equal to the H plus. Okay. And so I'm going to figure my H plus is equal to 10 to the negative 4.5. So again, this is not a whole number. So I need to plug that into my calculator as 4.5, hit the negative button, and then I'm going to hit on my calculator shift log because my shift log is 10 to the x. And this is going to give me a value of 3.16 times 10 to the negative 5 molarity. So here's another question. Determine the pH of a 4.26 times 10 to the negative 4 molar HCl. So notice when we look at this, is this an acid or a base? Well, our concentration of hydrogens in this case, because it's a 1-to-1 ratio, it's going to be 4.26 times 10 to the negative 4. So your H plus is 4.26 times 10 to the negative 4. So our pH value, our pH is going to be negative log 4.26 times 10 to the negative 4. So I'm going to type in 4.26 EXP negative 4, and then I'm going to hit log, and I'm going to hit my negative button. And that's going to end up giving me 3.37. Determine the OH minus and the POH of the HCl solution above. Okay, so I have my pH in that situation of my 4.26 times 10 to the negative 4. And so if I take my pH, which is 3.37, and my POH is going to be the easiest to find. POH equals 14 minus pH. So that's going to be 14 minus 3.37. And that's going to end up giving me 10.63. Okay. And then for my OH minus concentration is 10 to the negative 10.63. Or I can do 1.0 times 10 to the negative 14 divided by 4.26 times 10 to the negative 4. Okay. And that's going to give me 2.34 times 10 to the negative 11. Okay. And that would be a molar concentration. Okay, so here we have determined the H plus for the solution with a pH of 10.82. So to get my H plus is equal to 10 to the negative pH. So I have 10 to the negative 10.82. Okay, and so I'm going to type into my calculator 10.82 negative shift log. that's going to end up giving me a value of 1.51 times 10 to the negative 11 molar. So now we're going to move into a discussion of types of acids and bases, because here's the thing is I've given you this definition already, the Arrhenius definition. So this is important to know. This is the Arrhenius definition, is that acids are any substance that add H plus ions to a solution. And bases are any substance that add hydroxide ions or OH minus to a solution. So when you have your acids, you get your H plus and your negative ion. And when you have your bases, you get your A plus, whatever your ion is, your cation and hydroxide ions. And your pH equals 0 has more H pluses, and your pH of 14 has more OH minuses. But here's the deal. Then after some time, you had these guys, Bronsted and Lowry, and they came along and said, not everything fits into that definition. Remember, if you go back a little bit in this discussion, NH3 is going to be a base, but NH3 doesn't have any OH minuses. So what do we do about that? Or for example, calcium carbonate. Calcium carbonate doesn't either. So if we're looking at this, Bronsted and Lowry came up with a new definition of acids and bases in 1923. So what Bronsted and Lowry said is that an acid is a substance from which a proton can be removed, and a base is a substance in which a proton can be taken. Okay, so in this case, when I'm saying a proton, I'm talking about an H plus. Okay. So another way for us to look at this is acids are proton donors and bases are proton takers or acceptors. So in this case, we have ammonia. Ammonia is NH3. NH3 becomes NH4 plus. It took an H plus. Therefore, it is a base and it becomes a conjugate acid. Now watch H2O. H2O in this case goes from H2O to OH minus. It gave up an H plus. So in this case, water is actually acting as an acid and it becomes a conjugate base. So these are called conjugate acid base pairs. An acid, when it loses its hydrogen, it becomes a conjugate base. So the conjugate base has one less hydrogen, and the conjugate acid is when a base takes an H plus. So you have your base becomes a conjugate acid. A conjugate acid has one more H plus ion. So conjugate acids are produced when a base gains an H plus. Conjugate bases are produced when an acid loses an H plus. Your conjugate acids and conjugate bases are your products. Okay, they're your products. They're going to be in your product side. So those are produced. The conjugate acid and conjugate base pairs are in your products. So what is water? Well, water can act as either a Bronsted-Lowry acid or a Bronsted-Lowry base. In this case, it's acting as an acid. NH3 becomes NH4. So this was your base, and that's your conjugate acid. And water is acting as an acid, and it gives up a hydrogen. So now you have, instead of H2O, you have one H and one O, and this is your conjugate base. And for your base, water can act as a base. In this case, we have nitric acid becomes HNO3. So here's your acid. Water becomes H3O plus. So water is acting as a base. This is the conjugate acid. This is your conjugate base. And remember, we've already talked about hydronium ions. Hydronium ions are your H3O plus. So basically, your hydronium ion is really the conjugate acid of water. So we can also rewrite pH as pH equals negative log H3O plus. Now, when an acid reacts with water, a hydronium ion is produced. So Lewis acids and bases. Then came along Gilbert Lewis, and Gilbert Lewis came up with a third theory, and it's very general. Acids are an electron pair acceptor. They take electrons, and bases are electron pair donors. They give up your electrons. So a Lewis acid would be like H plus, and H plus is going to take electrons from your OH minus. So neutralization reactions. We've talked briefly about neutralization reactions, and I just want to go over it very quickly. Neutralization reactions are a reaction between an acid and a base in aqueous solutions, and they produce salt and water. So when you have your Arrhenius acid, HA, A represent your anion, MOH, M representing your cation, they come together to form your salt, okay, because you have a cation, you have an anion, come together, form an ionic compound, and water. When acids are mixed with acids, the pH remains less than 7. When bases are mixed with bases, the pH remains greater than 7. Now, when you're baking, you actually use acid-base neutralization type reactions. So here's an example. When you're baking and you want your really moist bread or your moist cake and you want all those bubbles in it, what you really have is you have baking powder that you use. Baking powder is going to cause your baked goods to rise a little bit more because what you have is you have sodium bicarbonate reacts with tartaric acid. So you have a base and an acid react, and they produce carbon dioxide in this case. So you can use acid-base neutralization to get a good rise or a good moistness in your baked goods. Okay. So here's the thing. We're not going to go over titration in detail, but I do want you to understand how much of everything do you need. So if you wrote the balanced chemical equation for KOH and HCl, you would end up getting KCl plus H2O. So what's the mole ratio of KOH to HCl? It's going to be a 1-to-1 ratio. So for every 1 mole of KOH, I need 1 mole of HCl to completely neutralize it. So if I have 100 milliliters of 1 molar HCl, how many moles are going to be used? Well, I have 1.0 moles per liter times 0.100 liters, because that's what a milliliter is. And that's going to end up giving me 0.1 moles of HCl used. So if 0.1 moles of HCl is used, how many moles of KOH are needed to completely react? Well, in this case, what we're going to need to completely react is we're going to need the same amount because it's a 1-to-1 ratio. So we have for every 1 mole of HCl, I need 1 mole of KOH to fully react and fully neutralize. So in this case, I need 0.1 moles of KOH. Okay, so that's going to just be our very brief discussion about neutralization reactions and what is needed to fully neutralize. It's all based on your mole ratio.